Hello, my name is Matthew Hill, and I've come to discuss the seven types of quadrilaterals. So, in this report, I'll discuss the seven quadrilaterals as well as give the examples of them, and also discuss some of the various mathematicians that have made contributions to developing the area of quadrilaterals, some of which include Euclid as well as the Indian mathematician Brahmagupta. So, what are quadrilaterals? Quadrilaterals are defined as four-sided polygons, and they are also referred to as tetragons. The sum of the interior angles of a quadrilateral is 360 degrees, and a quadrilateral can be of the type convex, concave, or not simple. So a concave quadrilateral is one in which one of the interior angles measures greater than 180 degrees. A convex quadrilateral, however, has an interior angle measures that are all each less than 180 degrees, both of which are considered simple quadrilaterals as opposed to non-simple quadrilaterals, which have a pair of sides that intersect at some point. So a quadrilateral can also be of the type cyclic, inscribable, and bicentric. So a cyclic quadrilateral is one in which a circle can be circumscribed around the quadrilateral to touch each of the vertices of the quadrilateral. And then an inscribable quadrilateral is one in which a circle can be inscribed within the quadrilateral and touch all of the sides of the quadrilateral. And so if a quadrilateral is both cyclic and inscribable, it's considered to be bicentric. And the area of a bicentric quadrilateral is equivalent to the square root of the product of the sides of the quadrilateral. And this report specifically focuses on the simple convex quadrilaterals. And the different types of these quadrilaterals include the square, rectangle, parallelogram, rhombus, kite, trapezoid, and the isosceles trapezoid. So the need for calculating area is kind of the basis or the beginning of quadrilaterals. In fact, it dates back to the early Babylonians, in which they needed a way of calculating a particular area of certain quadrilaterals. And the area that they found was, in fact, given a quadrilateral with sides A, B, C, and D, the area is equivalent to A plus C multiplied by B plus D divided by 4. While this equation only applies to the specific quadrilateral that they were dealing with, it does prove useful in giving the area. Moving along, it was actually the Greeks who first used the term quadrilateral to define a three-sided shape. And then it was later given to polygons that had four sides. And Euclid wrote quite a bit of work on quadrilaterals within his book, The Elements, including some talks on the square as well as parallelograms. And a general formula for cyclic quadrilaterals was actually given by the Indian mathematician Brahmagupta, and he used sort of a generalization of a formula obtained by Heron for the area of a triangle, and he kind of equated that to quadrilaterals, in which given a quadrilateral with sides A, B, C, and D, and the circle that is circumscribed around it to have semi-perimeter S, the area can then be found as the square root of S minus A multiplied by S minus B multiplied by S minus C multiplied by S minus D. And then a further generalization of that formula was found to be the square root of S minus A multiplied by S minus B multiplied by S minus C multiplied by S minus D minus the product of the sides multiplied by cosine squared of alpha plus beta over 2. Another development that was made by the Egyptians involved calculating the area of an isosceles triangle, and they did this by splitting the triangle into two right triangles and then joining them together to create, at the hypotenuse, to create a rectangle. And so by finding the area of the rectangle, they had found the area of those two triangles as well. And a famous mathematician by the name of Pierre Varagnon actually gave a formula in which he calculated the area of a quadrilateral given its midpoints that were connected to form a parallelogram within this quadrilateral, and it became known as the Varignon parallelogram. And its area is actually equivalent to 1/2 of the area of the original quadrilateral that he used. So the first type of quadrilateral to talk about is the square. And the square is defined as that which is both equilateral and right angle. And this is actually the definition given to it by Euclid within his book, The Elements. And the area of a square is recognized as S squared, where S is the length of one of the sides. Being that the square is equilateral, all sides are equal. So the perimeter can also be found simply by just adding all four sides or multiplying one of the sides by 4. will also return the perimeter of the square. And some of the classic examples in the use of the square is specifically using the Pythagorean theorem when equating two sides of a right triangle being also the side lengths of squares, and how the hypotenuse of this triangle will then be equal to the side length of a corresponding square. And the diagonals of a square actually are perpendicular and also bisect each other and form a pair, or they bisect the pairs of opposite angles. And their length is denoted as the square root of 2 multiplied by one of the side lengths, s. All squares have end circles, and this just means that a circle can be drawn within it to touch all the vertices. It's also known as being inscribable. That is, there exists a point in the center of the square that is equidistant from both the four sides and the four vertices, and it's due to this that a circle inscribed in the square is centered at this point will have a radius that is equal to exactly 1/2 of one of the side lengths of the square. So the next quadrilateral we're going to talk about is the rectangle. The rectangle is known for having opposing sides that are parallel and equal length, and every interior angle of a rectangle measures 90 degrees. There actually is a special case of rectangle, which is considered a square. So a square can be considered a rectangle, but not all rectangles are considered squares. And the diagonals of a rectangle are congruent and bisect each other at the point of intersection. Another interesting idea is that given a rectangle with its properties, it can also be classified as a parallelogram because it meets the criteria for parallelogram. And so there exists a special rectangle which is known as the golden rectangle. And this rectangle is based on the golden ratio, which is found as 1 plus the square root of 5 divided by 2, or 1.618, which is an approximation of it. And it's denoted by phi. So a golden rectangle is one with side ratios of 1 and 5. And this is actually determined based off of an equation of phi squared minus phi minus 1 equals 0. And given a rectangle with these side proportions, a square can be partitioned of length 1 by 1 out of this rectangle, and it will create another rectangle which is, again, of the proportion 1 to 5. And so these can kind of be endlessly done to form what is known as the golden spiral. And the decimal expansion of phi, or the golden ratio, actually consists of a series of consecutive digits which are prime, and these are referred to as phi primes. The next the next quadrilateral is a parallelogram, and in a parallelogram, opposite sides are parallel, and therefore opposite angles are also equal. And when the sides of a parallelogram are equal, then it's considered to be a rhombus. And if the interior angles of the parallelogram measure 90 degrees, then the parallelogram is also a rectangle, and therefore a special type of square. And if two congruent triangles are formed when the diagonal of a parallelogram, along the diagonal of a parallelogram, and they create consecutive angles which are supplementary. And the diagonals of a parallelogram bisect each other, and the area of it is equivalent to the length of the base multiplied by the length of the height. And it can also be found by multiplying two adjacent side lengths of the parallelogram together, and then finding the product of that and the sine of any one of the interior angles. And also another note is, given a parallelogram with sides formed by the vectors u and v, where vector u consists of ux, uy, and vector v consists of vx, vy, the area of that parallelogram will actually be equal to the cross product of these vectors, which is also denoted as the determinant of u and v, which is simply ux vy minus uy vx. And this cross product actually creates a vector that is perpendicular to those two vectors, and its magnitude is the area of the parallelogram. This can also be given as the magnitude of u multiplied by the magnitude of v times the sine of theta, where theta is the angle in between vectors u and v. So the next quadrilateral is a rhombus. A rhombus consists of parallel opposite sides, as well as all sides of a rhombus are the same length. And it is noted that opposing angles of a rhombus are actually congruent, and adjacent angles are supplementary. So given a rhombus of height q and length p, the area will be equal to 1/2 of the product of P and Q. And the diagonals of a rhombus are also perpendicular, and they bisect one another. And the lengths of these can be obtained by taking the cosine of the longer side and the sine of the shorter side of the interior angle formed from the diagonal, and then multiplying it by 2 times the side length. And as noted previously, a rhombus in special cases can also be considered a parallelogram. And the perimeter of a rhombus is found as the same as a square. It's just 4 times the side lengths of one of the side lengths of the rhombus. So the next quadrilateral is the kite. A kite contains 2 sets of adjacent congruent sides, and the diagonals are perpendicular and bisect one another. They create a pair of isosceles triangles at the top and a pair of congruent triangles at the bottom. And one of the diagonals also bisects the interior angles, and the kite has 1 set of congruent angles. A kite can be both concave and convex, but in this report I focus on the convex kite. So the rhombus is actually a special case of the kite. The area of kite can be found as 1/2 of the product of the diagonal lengths. And so given the equation for the diagonals, where one diagonal P is equal to the square root of a side a squared minus h squared plus the square root of b squared minus a squared. And the other diagonal Q would be equal to 2 times the height. And those equations give the lengths of the diagonals, and where A is the length of the longer side and B is the length of a shorter side, with H is half the length of the shorter diagonal. So the next type of quadrilateral to focus on is the trapezoid. The trapezoid is a type on its own, and it also has sort of 2 subtypes, which are considered the isosceles trapezoid, which is actually the 7th quadrilateral, and then you also have a right trapezoid. And so a trapezoid has 2 parallel sides, and it is also referred to as a trapezium. The area for a trapezoid can be obtained from the formula 1/2 a plus b times h, where a and b are side measures and h being the height of the trapezoid. And so the perimeter is actually equal to the sum of all the sides of the trapezoid, and the diagonals can actually be found by taking the square root of ab squared minus a squared b minus ac squared plus bd squared divided by b minus 8. That'll give one of the diagonals, and then the other diagonal will be attained by taking the square root of ab squared minus a squared b minus ad squared plus bc squared divided by b minus a. And that is with height given by the equation h equals n over 2 times the absolute value of b minus 8, n being 4 times the square root of s minus a times s minus b times s minus b minus c times s minus b minus d, where s is equal to 1/2 of a plus b plus c plus d. That's actually the semi-perimeter. The median of a trapezoid is denoted by m and is actually joins the midpoints of the legs of the trapezoid. And it's also parallel to the bases of the trapezoid, and its length is equal to half of the sum of the bases. The median also bisects the opposing sides to create 2 congruent adjacent sides. And the area can also be written as a product of the median and the height. A right trapezoid is one in which 2 of the interior angles are in fact right angles, and its area is 1/2 a times h1 plus h2, or ah2 minus 1/2 h2 minus h1a. And then the perimeter is given by a plus h1 plus h2 plus the square root of a squared plus h2 minus h1 squared, where h1 is the shorter side, h2 being the longer side, and a is the base of the trapezoid. The diagonal lengths for a right trapezoid are given as the square root of a squared plus h1 squared, and then the square root of a squared plus h2 squared. So the last quadrilateral is an isosceles trapezoid, and this one in which the base angles are equal and thus the legs are also equal. Due to the Pythagorean theorem, the measure of the height is equal to the square root of c squared minus 1/4 times b minus a squared. and this area is the same as a regular trapezoid. The perimeter is equal to the sum of the bases plus 2 times the leg, and the diagonals, however, are congruent and both equal to the square root of AB plus C squared. So in this, I've discussed various types of quadrilaterals, as well as giving some examples and some of the characteristics of these quadrilaterals, as well as their properties and some mathematicians associated with them.